All right. I want to start with this word problem and then get to the PV diagram and fill in this chart. Focus, good. Here we go. We have 0.125 mole of diatomic gas at 300 Kelvin and 100 kilopascals. For reference, that's about 1 ATM, right? 101.3 kilopascals is 1 ATM standard atmospheric pressure. So basically, standard atmospheric pressure, this is about room temperature, and we have this much gas. All right. And then we're going to try to heat it isochorically to some final temperature. And let me see if I have, all right. So when we run this thing, let's see what do we already know? Let's start with that. So P initial is 100.0, and then we have diatomic gas. And notice the temperature range in this problem is between 300 and 1,000. What does that tell us? We're in this temperature range for the entire problem, so F is 5. Let's get that up there. And then, aha, CV and CP. Once I know this, again, I'll go back to the other board. We know that these two equations, I can get CV and CP. So if we know F is 5, I'm going to get 5 halves and 7 halves, respectively. And I think I've worked those numbers out just so I don't have to punch in the numbers. Well, I guess it's probably faster to just type them up. But what did I get? 20.785 joules per mole Kelvin for this one. Then you add another R, 29.099. Is that legible? Close enough. All right, so I've got that. Now, how can I get the initial volume? I can't draw anything on here unless I can find the initial volume. If you want to pause the video and think about it, go for it. 3, 2, 1. Well, we are assuming the ideal gas law is valid for our PV diagrams in this class. If you're in a more advanced class, maybe you have to use van der Waals. Okay, whatever. So let's assume here P initial V initial equals nRT initial. We know nRT and P. We can crank this out. Be careful when you plug this in. This is 100.0 times 10 to the 3 regular pascals, because it's kilopascal, right? So if we're trying to get the volume in meters cubed, we need to convert that. R, for reference, remember R is 8.314 joule per mole Kelvin. I use that constant right here. All right, so when you punch all that in, just to save myself some time, you can do the math as well. What did I get for that volume? I got 0.003118. All right, and so basically 0.003. Aha! We can now label point A on here. It's basically, so if this is 0.002, so 0.003 is right here, so it's just a tiny bit above that at 100. So boom, we've got point A just above 0.003 volumes at 100 kilopascal. Great, moving on. What are we trying to figure out next? V final, P final, stuff like that. All right. Well, let's think. What do we know? isochorically. What does that mean? Constant volume. Aha! We know V final already. Sweet. This kind of reminds me of those magic square problems I did as a kid, right? Where it's a little puzzle. That's one of the reasons I think I like this section. Just, I don't know, it's like every problem's a lot of puzzle thinking, right? On test questions, I just rearrange the givens and you have to use the facts to kind of puzzle out what is known. That's a little bit like real life, right? You have some information and you're trying to figure out others and it keeps changing. It's classic. All right, how could I get P final? Well, the classic thing you do is take a ratio. You might just say, can't I just plug in the numbers again? Yeah, just a lot of times these ratios end up being fast. So let's just try it. And if I'm wrong, we'll just do it the other way. Why is this kind of handy? Well, this sentence implies we don't have any leaks. We have this gas. It didn't say any gas leaks out. If gas leaked out, this would be a harder problem. But so that means N is constant. It's the same between both. R is a constant. What else is a constant? The initial. So notice we get this quick ratio multiplying here. Solve for P final really quick. Pause the video or beat me to it. So it says P final should be T final over T initial. See if you got that. I'm going to punch in the numbers really quick. T final is 1,000 divided by T initial is 300. Notice we're not using Celsius, right? Because this came from P equals nRT. This does not have a delta T in it. Gotta use Kelvin. Can't use Celsius. All right. Times, what was the initial pressure? 100. So 333 kilopascals. All right. Q in. How am I going to get Q in this problem? Well, I know Q for a constant volume process is N CV delta T. Delta T, the change in temperature, is 700 Kelvin. N is 0.1250 mole. And CV, we've got that right here, if we need it. So in this case, you just punch in the numbers, 0.125 times 700 times, what was CV? 20.785. I like to keep extra digits on here. You might notice I'm keeping a lot of extra digits laying around. I don't want to cause rounding errors too soon, so maybe I should keep this one in here and indicate the rounding. But anyways, I've got 18.7. All right, and so what are we thinking here? 4 digits, probably 3 digits, this one, right? So we're probably off in the 3rd digit, so I'm going to indicate that. I like to keep the extra digits because when we get to cycles, right, there's a lot of little subtractions and the errors can add up. So I'll keep an extra digit in these problems on all my, I like to keep my unrounded work in my charts. That's it. All right, so work done by. Well, in general, we always know work done by the gas is equal to the integral of P dV. When V is a constant, V initial equals V final, there's no area under the plot. This should be 0. Finally, delta E internal, first law. Remember, delta E internal is equal to Q in minus work by. In this case, work by 0, it should just be Q in. Recall, there was a shortcut mentioned in the last video. you can always use delta E internal is the heat for a constant volume process. This also works here. So you could have just said, oh, I know this is the change in internal energy because that's true for any process, isochoric or not. The change in internal energy is always given by this, right? Assuming we're in one, okay, whatever. All right. So here, this is just 18.7, third sig fig rounding. Well, now we can make our plot. Let's get point B on here. It's the same volume, but now we're at 333, which is probably about right here. So there's point B. Now let's draw the process. It was going up like this. And then that's not good enough. You have to include the process area. Quick check. What's the area under that curve? 0. What's the work done? 0. That's an isothermal process. Not much else to say about, or sorry, that's an isochoric process, constant volume process. Not much more to say there.